like reactivate the license and it wouldn't work and it had made me reinstall it, so it's still installing. All right, so I have some problems here that I covered the concepts that you're supposed to know for the final exam. And if you read the email, I'm not going to answer the questions directly about the final exam, but I will certainly answer questions about these questions and the concepts in them. So if you need me to explain something in there that is related to an exam question, but that's because it's a concept in Circuits 2, I'm happy to do that, but I'm not going to answer questions about the exam or I'm not going to check your work or anything like that. So let me see if this finally worked.
It's so unreasonable looking.
Yeah, right. Okay, so this first one is we have a single-phase AC source with an RMS voltage of 230 at a frequency of 50 hertz. Find the angular frequency omega in the period in seconds. Find the amplitude of the voltage and write a time domain equation for the voltage in that form. And then write the corresponding phasor in RMS with magnitude and angle. So this should be reviewed from very early on in the semester. So when you have the frequency is given in hertz. So frequency is 50 hertz. And a hertz is a per second, or a second to the -1. And omega is angular frequency. And omega is 2 pi f. So it'd be 2 pi times 50. And that's going to be in radians per second. And 2 pi times 50, and you can check my math because I can't guarantee that it's right, but 314.2 radians per second. So that is the angular frequency, or omega. Now the period, the time for one complete cycle, that's capital T. The period is 1 over the frequency, not the angular frequency, because the frequency is cycles per second, whereas the angular frequency is radians per second. So 1 over 50, and
Okay to grab one that pronounce?
yes, 1 over 50 is 0.02, and if frequency is per second, then period has to be in seconds, so that is the time it takes for one cycle. All right, so we are given the RMS voltage of 230 volts. So VRMS,
It's 1 over 50 instead of 60.
that's just my bad handwriting. That's 50 in my
in
my handwriting. That's 50 or 60. You never know. That's what makes it fun. It could be either one. Okay, so VRMS is 230 volts. And so root mean square, which we're going to be talking about a little later as to what it is, it's one way of talking about a kind of average of things. So we have different kinds of averages. We have the arithmetic mean, we have a geometric mean, we also have the root mean square. And it turns out that for sinusoids, if you have something that's a sinusoid, then the VRMS equals the maximum voltage over the square root of 2. Now the maximum voltage is the same as the amplitude, because if we have a sinusoid, then the amplitude is this maximum distance, so that's the amplitude. And the root mean square is the maximum divided by, it's a little more than half. Yeah, it's somewhere around there. And so if VRMS is 230, then 230 equals the maximum divided by the square root of 2. Our Vmax equals 230 times the square root of 2, or 325.3 volts. Okay, so we want a time domain expression for the voltage in the form V of t equals V max cosine omega t plus phi, such that V of 0 equals 0 and V of t is increasing at t equals 0. Okay, so we want V of t to equal V max cosine omega t plus phi, and we want V of 0 to equal 0, and we want V of t to be increasing at t equals 0. So
That would determine the phase angle.
so if I plug in 0, V of 0 equals Vm cosine 0 plus phi. So this is actually going to get us our phase angle, equals Vm cosine phi, and we need that to be 0. So where is cosine 0?
Like pi over 2 or negative pi over 2.
Yeah. Pi over 2, or negative pi over 2, or 90 degrees, plus or minus 90 degrees. So that's going to be what phi is. Now, if we want it to be increasing, that means its derivative needs to be positive. So V prime of t equals, so the derivative of cosine is minus sine, so Vm minus Vm sine omega t plus phi, and then the chain rule says multiply by the derivative of the inside. That would get me omega. So I need this to be positive, so I need this to be greater than 0. And I know that at 0. And if I plug in 0, get minus Vm omega sine phi. And what was phi? Phi was plus or minus pi over 2. And which one of these would make this positive?
Pi over 2.
So when we are at negative pi over 2, that becomes positive. So we would write this as V of t equals write like this first, Vm cosine omega t plus phi, and so that would be 325.3 cosine. Omega, we found that to be, did we find that? Yeah, we found that.
Yeah.
314.2. 314.2 T minus 90 degrees. And you do have to put the degree symbol in here. So when you have a degree symbol, it's degrees. If you don't have a degree symbol, it's radians. But we use degrees usually in phasors. And so as a phasor, we would get that the RMS phasor equals V RMS angle phi, and V RMS was 230 angle negative 90 degrees. And don't forget your units. I often forget units when I write an equation. It's like I don't forget them when I have like a single number. When it's equation, I just forget it, but they're still there. So that part's important. Okay, so any questions on that one?
So for the time domain, we want to use the max over root 2, and for the phasor, we'll use the regular V max, not the divided by square root 2.
Well, what did the problem say? The corresponding phasor in RMS form. So it specifically said RMS, so it depends.
Okay.
Yeah, so you could have it either way, but yeah. Any other questions? All right, everybody good with that? Okay, all right, let's go into the next one. Any Zoom questions? Oh, I've got James. He's responsible for that, right? Tell me if there are any Zoom questions.
Yeah.
Yes.
I have a more general question where sometimes I understand that I get a bit tripped up about phasors because I understand that's more or less a simplified form of how do I represent this waveform.
Mm-hmm. So what a phasor is telling you? Oh, I'm sorry, I interrupted. What was your question?
Well, it's more so I'm just saying that I have a general unease about them where just jumping between forms, jumping from this form to the phasor into the exponential form. I understand mathematically what we're doing. It's just sometimes I feel like I lose the plot, and it's just a black box that I use.
Well, it is a way to simplify calculations. We do it because this phasor is not representing. This is the RMS phasor for this voltage right here. But this voltage is max. So if I wanted to say what the max was, then I would write it as 325.3 angle negative 90 degrees. And that would be the phasor that corresponds with this one right here. This is the root mean square phasor that I wrote up here. This is the phasor that represents the maximum. And the information you lose when you do this is the frequency. So when you have it as a phasor, you don't have the frequency anymore. So you don't have that, but it does make them easy to work with because since these are, you can work with them as like exponentials, and so this in phasor form, when you multiply two phasors, you add their degrees together, and then when you divide one phasor by another, you subtract them, and that's because you're looking at the exponential form of the trigonometric equation up here. It just makes it easier to use. And so all I can really say about your unease is, yeah, it's understandable. It is kind of weird at first, but you kind of have to just keep working with it. And when you do, when you write it, you just always kind of ask yourself, what does this mean? And why am I using it? Because there are times when, like if I had 4 plus J2, and I needed to add that to 23 angle 32 degrees, then I have one of these in A plus JB form and the other in polar form. Which one would I want to use to do this calculation?
I prefer the rectangular form for addition.
Yeah, for addition, so I'd change it to rectangular. And if I wanted to multiply, it'd be easier to change this one and have it as a figure. So it just kind of depends. So I don't have a good answer for you to say don't feel uneasy about it, because it's reasonable to feel uneasy.
All right.
And the other reason that we use this here is because this phase becomes very important when you start working with AC, because now that's the whole point of AC is things are not always, they're not always in the same phase in DC. This doesn't mean anything, but here you have to pay attention to those. So, all right. Moving on to problem 2. So here we're going to talk about what do we mean by root mean squared. And how do you calculate it? Okay, so something does not have to be periodic for it to have a root mean square, but it'd be difficult to calculate, I guess, without it being periodic. Now, if it's a sinusoid, you know how to get the RMS value. The RMS value is the maximum value divided by the square root of 2. But just because it's periodic does not mean that that's going to be what it is. And so the definition of root mean square is as follows. So RMS equals the square root of 1 over the period, so it's periodic, so you need to know what the period is, of the integral from 0 to t, so for one period of I squared t dt. So that's I just because the question said for a periodic current. Explain in words what the RMS value means physically. What does it tell you? Okay, so it is the equivalent DC power that would deliver the same average power as, I'm sorry, the equivalent DC value, not power value. So because I was specifically talking about current here. The equivalent, so here would be the equivalent DC current. The equivalent DC value that would deliver the same average power as the periodic value. So if the current is I of t and I is periodic, then the power equals I squared RMS R, the current through a resistor. The current through a resistor is I of t and I is periodic, and the power is I RMS squared R. And so that's what the meaning of the root mean square is. So it would be the current, the equivalent DC current that would deliver the same power. So now, let's say, let's compute some. So we're going to do two examples here. So example C is going to be I of t equals some constant, I naught. We could say 5 or 1, but we're just going to use a constant. And so we'll write I RMS equals the square root of 1 over t times the integral of 0 to t of I naught squared dt. Now, you might be saying, well, what's the period of a constant function? So here's I naught. What's the period? Well, you can choose any period you want. So a period means the amount of time it takes it before it comes back to its original place. Well, that's for constant, that'd be any time. But because of that, we can just use t. It doesn't matter. We could use any value. We could make t any value we wanted, and we would get the same answer. So I'm just going to use t. This will be the square root of 1 over t times the integral of I naught squared is I naught squared t from 0 to t. This is 1 over t times t cancels each other. Well, I'd plug in t, so I'd get 1 over t times I naught squared times t. 1 over t and t cancel, and I have the square root of I naught squared, which is just I naught, which makes sense because I said the root mean square is a kind of average, and a constant function shouldn't have any average other than itself. That would be weird.
What is I naught again?
It's just a number. It's just constant.
Constant. Okay.
It's just a constant. So if our current was 5, the root mean square would be 5. If our current was 7, the root mean square would be 7. If our current was 0.01, it would be 0.01. Okay, so now let's say we have a sinusoidal current that is a cosine. So, and I already gave away the answer to this earlier. I said what you get anytime you have a sinusoid, but we'll see why that's the case. So we have I of t equals Im cosine omega t. So then I RMS equals the square root of 1 over, what's the period for a cosine?
Also t.
What's that?
It's also t.
Well, you're right. We can just say t. It would be 2 pi over omega.
2 pi over omega. Because it's 2 pi f 1 over t, so isolate and be omega over 2 pi.
I know that the period.
And it's 1 over f and omega equals 2 pi f.
Equals 2 pi. Yeah. So the period is 2 pi over omega.
Yeah.
So this is 1 over, but I'm just going to put t here. So, but I will say here, period is 2 pi over omega. So 1 over t times the integral from 0 to t of im squared cosine squared omega t dt. So I RMS equals the square root. So 1 over t would be omega over 2 pi. I can bring the im squared out. Have the integral from 0 to t of cosine squared omega t dt. Now you can use MATLAB or whatever you want, but I'm just going to be old-fashioned. And if you remember way back from Calc 2, cosine squared omega t equals 1/2 times 1 plus cosine 2 omega t. So this would be the integral from 0 to t of 1/2 times 1 minus cosine 2 omega t dt. Take the 1/2 out, you get t. Integral of cosine is sine, so minus sine 2 omega t over 2 omega, 0 to t.
Is it minus or plus?
Oh, did I put I don't know why, that should be a plus. Equals 1/2 t plus sine 2 omega t over 2w minus, if I plug in 0, do I get 0? Yes. Right. Well, or you can remember that the average value of cosine over half the half of its period is 1/2. But let's see, what have I got? What am I doing wrong here? Maybe nothing. Okay, so I've got omega over 2 pi times im squared times 1/2 times t was 2 pi over omega. Plus sine 2 omega t. Now what is sine 2 omega t going to be? What was t?
T was 2 pi over omega.
But what was it actually?
Oh, 1 over f.
Well, what is the period? I mean, sorry, what does t mean? It's the period, and what it's when it repeats itself, and so it's going to have the same value at t as it had at 0. And what's the value of sine at 0?
1.
0.
Or,
0.
yeah,
0. So this becomes omega over 2 pi times im squared times these 2's will cancel, and I have pi. Oh, it does work out. Pi over omega plus 0. And then my pi's cancel, and my omegas cancel, and I get im squared over 2. But if we recall, all that was supposed to be under a square root.
Yeah.
This is a 1 over lambda.
1 over lambda. That's a crossed out 2.
Oh, I was like, oh shit.
That's a 2. I am over the square root of 2. And so, like I said, if you have any sinusoid, the root mean square should be the maximum value divided by the square root of 2. And lucky for me, it turned out to be correct. Yay!
Just a math question.
Mhm.
So the reason when we in the previous thing we had defined IRMS equal to that like square root of 1 over t and then the integral. The reason that we don't run into some issues with the 1 over t being undefined when you actually evaluate that is because it can be expressed as omega over 2 pi. There's no 1 over 0.
Well, also the period is not going to be 0 because that doesn't. A periodic function has to have a period greater than 0.
Right.
So t will never be 0 if it's periodic. And yes, you can also always write it as omega over 2 pi. And yeah. Okay, other questions? All right. Going on to number 3. Given R equals 4 ohms, and the period is 8 milliseconds, and we have this function here, v of t, is defined as a piecewise function.
P-Spice?
P-spice? No. A piecewise function. So it's 10 volts from 0 less than or equal to t less than 0.002. Oh, by the way, let me just show you all this as well. Oh, it better let me sign in this time. I'm going to be angry. Don't have any code. I don't understand. Sorry. If I don't do this right now, I will never remember. I was going to show you how to do that integral on the little calculator, but I can't because I can't use the calculator software. So, but you can do those the integral like that on the little TI 36X Pro calculator. Okay, so we had 10 volts from 0 to 2 milliseconds, 0 from 2 milliseconds to 4 milliseconds, -5 from 4 milliseconds to 6 milliseconds, and 0 from 6 to 8. And we will want to, and it's saying it's periodic with period t equals 8 milliseconds. So it would repeat this same pattern every 8 milliseconds. So the first direction is to sketch it. So 2, 4, 6, 8 in milliseconds. -5, 10, -5, -10, and it was 10 from 0 to 2, and 0 from 2 to 4, and -5 from 4 to 6, and 0 from 6 to 8. And we're supposed to compute the RMS value of V. So the RMS value is going to be the integral of 1 over t. I'm sorry, the square root of 1 over t times the integral from 0 to t of v squared of t dt. So this will be (1 over 8) times the integral from 0 to 2 of v squared dt plus the integral from 2 to 4 of v squared dt plus the integral from 4 to 6 of v squared dt plus the integral from 6 to 8 of v squared dt. Because an integral is just a sum, and so you can break it up into parts and then add them up and get the same value. And so then we would get that VRMS equals the square root of 1 over 8 times the integral from 0 to 2 of 10 squared dt plus 0 plus the integral from 4 to 6 of -5 squared dt plus 0. RMS equals the square root of 1/8 times 100t from 0 to 2 plus 25t from 4 to 6 or the square root of 1/8 times 200 plus 150 minus 100. So the square root of 1/8 times 250 and I get 5.59 volts. Let's see, anywhere in here did I use milliseconds, and should this maybe not be volts? Let me think. It all cancels out. So yes, I did use milliseconds instead of seconds, but the reason that it ends up being okay is because my milliseconds I was plugging in here for my time, but I also had this 8 was also milliseconds, and so my milliseconds canceled with my milliseconds, so I didn't have to actually, it was fine to use 8 instead of 0.008 and 2 instead of 0.002 because the millis canceled out.
But would that second integral part be negative instead of positive?
No, because if you look, it's 1 minus 5 squared dt, so that minus makes it a negative, or like 1 minus negative 25. So
Well, there's no minus. It's just negative 5 in parentheses squared.
This is RMS.
if you scroll up to the integrals, you see v RMS equals 1/8. It's the second one.
No, but that's
From
my
46.
bad handwriting. That's a parentheses.
Oh, that's parentheses. Okay. I thought that was 1 minus.
Yeah. Sorry. No, it's parentheses.
So it would always be positive?
It will be positive because it's going to be positive. It's going to be positive on purpose because it needs to be positive to take a square root. So you're squaring. That's one of the reasons why you're squaring. That's why you square inside, because you're going to square root outside, and you need to make it positive.
So you don't get crazy numbers.
Right. Okay, and then the next part says to find the RMS current. Well, we don't have to do anything crazy here. If we have the RMS voltage and we were given a resistor value, which was 4 ohms, everything you know from circuits 1 works with RMS. And so if you know that voltage equals current times the resistance, then VRMS also equals IRMS times R, or IRMS equals VRMS over R, or IRMS equals 5.59 volts over 4 ohms, which is 1.4 amps. Similarly, when you're looking for average power, and we're going to talk about different kinds of power later on, but average power is V RMS squared over R, your resistance. This in our particular circuit here just has resistance. It doesn't have any reactants. And so this is going to be, our VRMS was 5.59 squared over our resistance was 4. And that gets us about 7.81 watts. Okay, how's that? So do y'all feel comfortable doing the RMS question on your test now? I can't help you with it, but do you feel RMS-y good?
I mean, I remembered it was a thing. I won't lie, I rediscovered during the test that I did not remember what it was.
But now do you remember?
Yes.
Okay.
When you're establishing the peak, or the period rather, you're going to look at the T0 and then go to till you hit another T0, or are you going to go from the peak to the peak?
Okay, so that's an excellent question. It's asking, how do I determine the period of a function, or how do I determine a period,
Of like a non-sinusoid.
right, a non-sinusoid?
It's the
Let
same
me,
idea, but
yeah, I just want to make sure I'm not doing the exact same one. So no, I'll do a kind of sawtooth. Okay, so I'll do one that's,
That's average power. It's not like
it is the same. It turns out to be the same. Are you setting like from power later on that we're going to do?
I don't know. I don't understand the difference between that average power and then power equals 1/2.
There is not a difference. Okay, tell me what you just said. Power equals.
The VM, IM, cosine, theta V minus theta I.
That's not what you just said.
1/2.
Okay, tell me what you. So 1/2 VM IM.
Cosine and theta V minus theta I.
Okay, so what you're, so I told you I was going to relate this to power later on,
Okay.
and I am, but I am going to make a real a point here. So let's say that we have no our phase. We're in phase, so our voltage and our current both have angle 0.
So that would be 1.
So that'd be 1. So in that case, I would say P equals 1/2 V max and I max. So what did we say VRMS is?
That's right. So it's just going to be that square root of 2, that's square root of 2, and then so the 2's are going to cancel it out. It's going to be left with V and I. Okay, I got it.
Mm-hmm. But most people don't, so I'm going to go on.
Okay.
Okay, because I get asked this question a lot. VRMS is V max over square root of 2, and IRMS is I max over square root of 2. So if I take VRMS times IRMS, that's the same as taking V max over the square root of 2 times I max over the square root of 2, which is the same as V max times I max over 2, which is the same as 1/2 V max I max. And so your question is, when you look at all your power formulas, sometimes it seems like there's a half and sometimes there's not. And it's just, where is this 1/2 coming from, and why does it seem to show up when you're not expecting it? If it's the 1/2 is not there, it's because you're dealing with RMS, and if it is there, it's because you're dealing with max values. But I still haven't answered the question that I started with, which was finding the period. So we want to find.
Can I give one quick question though?
No, because I'm in the middle of answering this question. And he already interrupted once, and so I'm not letting him interrupt again.
Sorry,
Because
I used up the interrupts.
Okay, so usually a way to measure a period, a good way to measure a period, is in fact peak to peak. But the reason why is what you're saying is it's the distance over which you have one complete cycle. And it's, you have to be a little careful. Like, I wouldn't want to say, like, from 0 to 0, because that might not be a full period. So I want to go, like, once you've gone through the entire cycle and you're back to where you started, and you're going to be continuing on in the same direction. So like with this one, here I go down to here, I'm back to where I started, but from here I'm going up, and from here I'm going down. So that's not a full cycle. When I get back to here, now I'm back to where I started, and I'm starting over again.
Right, so
So-
that would be your period.
So that'd be my period. In this one, I could go peak to peak, and that would give me the period. I could also start here and go to here, and that would be a period.
But you could also start at that negative
Yep.
and go from like that negative point all the way until, well, I was talking about where it starts. You could go from where it starts on the, like the sawtooth, right where the waveform starts, and then where that value occurs again.
Yes.
So it goes up, it dips, and then it occurs again, kind of like at the same value.
Right, but I have to go to here because instead of here, because here it's going down.
Right.
But I have to go back here because there it's going up. Is that what you were saying?
Yeah, that's what I was saying.
Yeah.
Like I'm saying, it doesn't matter necessarily where you start to observe it. It just matters that like you stay consistent with that value.
That's right. And then if you do that, it doesn't matter which period you choose, you'll get the same integral. So whether I go from here to take the integral, or if I go from here to here, if I have one complete cycle, I will get the same value for the integral.
In the first one, wouldn't your integral be negative in a sense?
This one right here?
Yes.
Well, remember, I'm actually going to square it before I take the integral. So,
Right.
this one would be 0 actually. But when I square it, this comes up here, and I get a half. Yeah. So when you square it, it changes it to make it positive.
Okay.
Okay, I'm going to pause this recording, and y'all are going to help me remember to unpause it when I come back. And I'm going to go to my office for a minute, and when I come back, we'll do the next problem. Wait, you had your question. Sorry.
Oh, I wanted to ask how the VRMS, IRMS relates to the, like a DC baseline for like any sort of voltage or current.
Mhm. So the VRMS, IRMS equals the average power. And so that would correspond to the power that you would get from an equivalent DC circuit.
So,
Effective.
Hmm?
Effective.
Effective, yes. So a DC circuit that had a voltage of this VRMS.
I didn't get the effective DC equivalent.
Yes.
Alright, so if I just, gave voltage a additional 5 volts of baseline, a DC baseline, that would just be the VRMS that we already have, plus 5. Or we recalculate it, but pretty much that's it. Alright.
Yeah, I mean, maybe. I mean,
If it were DC, then maybe, but
if it is
otherwise,
DC, right, but if I add 5 to something, I'm not going to get the same RMS plus 5 because of that squaring and integrating and all that. So like if I take the integral of sine squared of t, and I compare that to the integral of dt, compare that to the integral of sine of t plus 5 squared dt, that's not going to be just the same thing plus 5. So I'd have to think a lot about that, but I don't think that's exactly true.
Yeah, so this is not like a, I guess it's not a linear relationship, you would say?
No.
Alright.
Okay, so I will be right back. All right. All right, so now we're going to look at problem 4. We have an AC source, and we have a parallel resistor, inductor, and capacitor. And we're going to find out some various different things about it. And then you can ask me general questions. And we'll move on from there. Okay, so we have the angular frequency, omega is 1,000, and we need to compute the complex impedances ZR, ZL, and ZC. So you just need to remember the formulas for impedances here. So ZR just equals R, and so that's 10 ohms. Zi equals J omega L, or ZL, sorry, ZL. J omega L, which is J times 1,000 times 20 over 1,000, because it's 20 millihenries. And so that is J 20 ohms. And impedances are all in ohms. And then ZC is minus J over omega C, or minus J over 1,000 times 100 times 10 to the minus 6, or ZC equals minus J, so that's 10 to the third times 10 to the second would be 10 to the fifth, times 10 to the minus 6 would be 0.1, which would be minus J 10 ohms. Make sure I got all those right. J20 minus J10 and 10. All right. Write the phasor voltage RMS at node A. Okay, so when you look at the voltage that's given, it's not RMS, and so that means your peak voltage is 100. So that means that VRMS, the magnitude of VRMS, is 100 over the square root of 2, is 70.71. And in our function, we don't have a phase angle, so VRMS as a phasor is 70.71 angle 0 degrees volts. If it did not say RMS, then you could just say 100 angle 0. But it does say RMS. So now we're finding the phasor currents, IL of R, IR, IL, and IC through each element, and the total source current IS. So how are we going to go about doing that?
They all have the same voltage.
And why do they all have the same voltage?
They're in parallel.
They're in parallel. So they all have the same voltage across them. So that means that they all have the same RMS voltage. And so the current, so V equals I times Z. Or I RMS will equal V RMS over Z. So I L, or IR, I'll start with IR, equals 70.71 angle 0 over R, which is 10. So that's 7.071 angle 0 amps.
Now, on this one, there was no mention of what current value we were looking for. Like, it's not IRMS. Would we, is that just, I mean, is it just assumed that we're looking for
It is on
IRMS?
this, because it would be total relevant.
Oh, is that what that is?
Yeah, that means the RMS value,
Okay,
and then the total IS is just how we all of these added up.
I didn't see, I didn't pay attention to that too.
Yeah. On if it did not say RMS, if nothing in the problem said RMS, then there's no reason to do RMS.
For the voltage?
Yeah. Yeah, I don't see any reason that you would. So, if it doesn't say RMS, just don't use RMS. Just use the regular one. Okay. So, that wasn't. It was IR RMS. That was it. IR RMS. I was like, why did I leave off the MS? Okay, and then IL RMS would be 70.71 angle 0 degrees over J20. Now, I know that J, if something is purely imaginary, then that means its angle is either positive 90 degrees or negative 90 degrees. If it's a positive J, it's a positive 90 degrees. If it's a negative, it's a negative 90 degrees. So this is the same as 20 angle 90. So this would be .536. Say 3.5 angle negative 90 degrees. And then IC RMS is going to be 70.71 angle 0 degrees over the impedance of the capacitor, which was minus J10. So that's 70.71 angle 0 degrees over 10 angle negative 90. So that is 7.071 angle positive 90. Now, the way this circuit was drawn, we just found each of these currents, and it's asking for the source current. And so by KCL, we know that all of these currents have to add up to be the source current. So IS RMS equals 7.071 angle 0 plus 3.5 angle negative 90 plus 7.071 angle positive 90. Now, I could do this on my calculator, but I'm not going to bore you again with how mad I am about not being able to use my calculator on my computer, but I can easily change these to rectangular because negative 90 degrees means negative J. So this is negative J 7.07, and angle 0 is just real. So then I get 7.071 plus, that would be 3.57, about 3J 3.57. And that would be the rectangular form. And then to get the polar form, I would just use my calculator to do it, but if you want to get the magnitude, it would be the square root of 7.071 squared plus 3.57 squared would give you the magnitude, and the angle is going to be the inverse tangent of 3.57 over 7.07, and that will be the correct value because these are positive, and that'll give us the first quadrant value. So this would be $7.92. And 26.8 degrees, 26.7 degrees maybe. So I source RMS equals 7.92 angle 26.7 degrees. Now, compute the average power absorbed by each element, which elements absorb real power, which elements absorb zero average power. Okay, so average power, is IRMS squared R, and this is the magnitude of your current. And it is RMS. If it was not RMS, then you'd have P average equals 1/2 I squared magnitude of I squared R. Now, what is R for the resistor? So the current for the resistor, what did we get for the current for the resistor? What was it?
7.071
Okay, so the magnitude is just 7.071 squared, because this is magnitude here, times, and the resistance was 10,
Yes.
and that's about 500, I believe, 500 watts. The real power, which is another name for average power, equals 0 for the capacitor and inductor. Because for the capacitor and the inductor, there's no R. I mean, you can't have no power there because they don't have the resistance. So they have reactive power.
So it's a sine wave, and then you find the average of the sine wave.
Right. Exactly. Okay, so now for a phasor diagram. And this is going to be a little harder for me. Just, I wish that the previous professors who taught the class did phasor diagrams, because I think they're really helpful. But the ones that I had and the ones that I've SI'd for didn't. So I haven't done a whole lot of phasor diagrams. I wish I had. I think they're really good to do. So let's do this. We've got our Our voltage had angle 0. And what was the magnitude of the voltage? $70?
70.71.
So even though these will be representing different units, we still try to do them proportionally to the numbers unless it's like way not, doesn't really make any sense. Okay, so this was V. I for the resistor was also at 0 degrees, and I for the resistor was 7.
7.07. No.
And I for the inductor, so IL lags V by 90 degrees, because IL was 3.5 minus 90. So the current for the inductor lags the voltage by 90 degrees, as inductors are wont to do. Whoops, that's too long. And the current for the capacitor leads the voltage by 90 degrees. What was the capacitor current?
7.071.
Okay.
It should always just be the opposite direction of IL.
IL and IC are always pointing in opposite directions, correct? Now, am I going to do IS? I don't have IS in here. I will. IS is 7.92 angle 26.7. So does IS lead or lag the voltage? It leads. So overall, this is I don't know what I'm trying to say. Yeah, yes, so overall it is more capacitive. And if we got the total, did we get the total impedance? Oh no, we didn't, because it was it's in parallel. Okay, that's I was like trying to figure out where we had like, but it was in parallel, and we never computed the equivalent impedance. And so without computing the equivalent impedance, we could say if we did compute the equivalent impedance, would the imaginary part be positive or negative?
Negative.
And why do you say that?
It's more capacity.
Exactly. Okay.
Because I said so.
Okay, so before we go on to the next one, do you have any questions on things that you would like to ask about this question? Things that, things that you'd like to know?
We expect to a lot of time of the lead class.
We did. Okay. So ready to move on to maximum?
I have a question
Yeah.
about like how do we determine power supplied or absorbed, like what that means, I guess conceptually.
Okay, so power supplied or absorbed. So when you how do you do that for a DC circuit?
Let's go on.
Okay, so for a DC circuit, if I'm trying to find the power across an element, then I would say that power equals IV, where I is the current. And so I take the current, and then if I am entering into the negative side of a voltage source, then I would make, like if this was 10 volts and this was 5 amps, that power would be 5 times negative 10 volts because I'm entering into the negative side of that 10 volt voltage source. If over here this was 0 and this was 10, and I have my current going through here is 2, then on this resistor right here, the V across that resistor in the direction of this current is a positive 10, and so that power would be 10 times 2. And so you take the sign of the voltage there, and if you got a positive power, that would be absorbed, and a negative power would be supplied. Now, resistors always absorb. So resistors absorb power. That is always the case. Power supplies can absorb or supply. depending on, like, if I have a power supply and my current is coming into this side and it's a positive current, and this is 10 volts, and that's a positive current, then this power would be a positive 20 volts, which means it is absorbing, so it's like it's charging. So you can have power supplies that charge. Now, with elements like capacitors or inductors, it says, okay, think about this for a minute. Excellent question, and not one that I had ever been asked before. So, if I want to find the power for a power source, so I know what a resistor does. A resistor is going to absorb. But if I want to find the power for the power source, I'm going to want to find its voltage and its current, and I get that power is still going to equal the voltage times the current. And then if you are looking for this at a particular time, you could plug in a time and actually compute the product and determine whether the power was positive or negative, and therefore whether it was supplying or absorbing. So if I had to figure that out, that's what I would do. So I would get an expression for the voltage, an expression for the current, and then I would just say I would assume at time 0, so plug in 0 and then go with the phase and then find these out and multiply them together. And if it's positive, it's absorbing, and if it's negative, it's supplying. And I believe that should help you out.
So if you want to figure out for a given source, you have to compute it at like the same time to compare two of those sources.
Exactly.
And it will come down to kind of like what the phase of it is at that moment.
Right.
Because that's going to change your phase angle difference.
Absolutely. And so if you are computing, if let's say you had a circuit, for example, that had 2 power sources, and you're trying to do this, if you compute it and you find out that they're both absorbing, you know you did something wrong, because you can't have a circuit with 2 power sources that are both absorbing. Now, one absorbing and one supplying is fine. It's possible they can both be supplying at the same time.
Yeah, I guess I'm just kind of confused because if you think of it, it seems like conceptually they're oscillatory. So like at one point you're going to have some positive current and some negative current. So you would think, oh, well, wouldn't it just be their magnitude, right? Because if this one is greater than this one, then I just know when this is positive, this will have a less positive, right?
Right.
But it actually depends on the phase more, because if this is supplying positive and it's greater, but this is negative at that time, then you know, oh, hey, this one is supply, this one is the absorption because it's out of phase.
I think that you must be really smart, because what you described was exactly what went through my head. And if that's exactly what went through my head as I was trying to figure out this question, then I'm just going to say you must be really smart. That's the same thing I was doing. So yeah, so that is I agree with you. That was the same conclusion I drew,
Well, I'd rather that, because it's like if I were writing this on an exam, I would rather write the conceptual synopsis than like just show it like algebraically, like, well, these numbers are here, so I mean that's more concrete, but it's like even without looking at the numbers, like the concept will hold true.
Right. And it is not usual that you would have, in circuits 2, it is not usual to have components, to have two power sources. Oh, no, that's not true. I take it back. No, never mind. That's not true. They definitely have different phases. So that is possible. So, okay, other questions?
I definitely. I'm sorry. I realized I left my, no, that's right. Sorry, I thought I had a sweater at the EFT.
Oh.
I'm sorry.
Any other questions besides where your sweater is?
Do we have time to do 5 and 6?
Oh, yeah. I just other questions on this before we go. Okay. So I had put this on here before I uploaded it. I was trying to make sure that I had the concepts that were on your exam, so I did not mean to actually have written on here. I think the one that I've uploaded does not have written on it exam problem number 5, but so for this one, we're going to be talking about maximum average power transfer. And you may remember from circuits 1 that you get maximum power transfer when your load resistance equals your Thevenin resistance. And same thing is kind of true for AC circuits, except remember that real power comes only from the resistance, and any reactive power that you're getting from an inductor or a capacitor is going to take away from your real power. So you would want your load to be the complex conjugate of your load impedance, to have the complex conjugate of your circuit impedance. And so we have a Thevenin equivalent circuit as shown below. The open circuit Thevenin voltage is V Thevenin is 24 angle 0 volts RMS, and the Thevenin impedance is 4 plus J3 omega. So if it's 4 plus J3 omega, we know that the resistor is 4 ohms, and the inductance J omega L equals J3. So omega L equals 3. Set the condition on the load impedance in terms of Z Thevenin for maximum average power transfer to Z load. So in order to get maximum power transfer, when Z load equals the complex conjugate of Z Thevenin. And that little star means complex conjugate. So in this instance, the load that would give us maximum power transfer would be 4 minus J3 ohms. So what we would have So if this was our original circuit here, so this is R and this is L, then what our load circuit would look like to get maximum power transfer is we would have the same ZR here, and if this is ZL, then we would have our capacitance ZC would equal minus ZL. So if we had an inductor here, we'd add a capacitor here, and that way we would cancel out the imaginary parts, and then our circuit would have essentially just a real impedance, and then we get maximum power transfer.
So it's going to be, I mean, the RC over here, then it would be ZL with the ZR to, I mean, for ZL, it would be ZC plus ZL.
Yes. Yeah. Oh, I'm getting confused because I'm putting L for inductor as well as for load.
I understand.
Yeah, so Z load. This is load, not inductor. So Z load is ZR minus ZL, whereas ZL is minus ZC. Okay, so once we have found that out, then there's just a nice easy formula for maximum average power. So the maximum average power equals the magnitude of V Thevenin squared over 8 R Thevenin. And this is the same as it is in DC circuits. And so in this particular example, the magnitude of V Thevenin was 24, so that's 24 squared over, oh, that's supposed to be Z Thevenin, times, I'm sorry, this is R Thevenin. It's R Thevenin because we got rid of the imaginary part. So 8 times, and then the resistance was 4. So 24 squared over 32, which is 18 watts. Let's see if I did everything I wanted to do. I don't think there was any way for me to go over maximum power transfer without going over maximum power transfer. And I think your test question just asked you about maximum power transfer in the meeting. So, any questions on maximum power transfer?
I do. I don't understand why the conjugate, having the conjugate of a second resistor would give us the maximum power transfer.
It's not the conjugate of the second resistor, it's the conjugate of the whole impedance. So remember, an impedance has a real part and an imaginary part. The real part is the power. The imaginary part is reactive power, and when you have reactive power, that takes away from the real power. So you want to have, if you want maximum real power transfer, you want to have 0 reactive power. So 0 reactive power would mean your imaginary parts are 0. So you want your total circuit to have, so if our impedance is R plus JX, this JX part here, that part is going to, the more that is, the less your real power is going to be and the more your reactive power is going to be. So you want this part to be 0. So you want this to be 0. So let's say your original circuit, Z7, is 8 minus J2. You proved in Circuits 1, or it's in the Circuits 1 book, that you get maximum power transfer when your resistance of your load is equal to the R Thevenin of your source. So we know the resistance would need to be 8, but we want our imaginary part to add up to be 0. So then if we make Z load equal to 8 plus J2, then our Z total is 8 plus J2 plus 8 minus J2, or 16, which is entirely real. So when you make it the conjugate, when you add it in, it makes the imaginary part add up to 0.
If they're all in series.
Well, it is if we're talking about Thevenin
Yeah.
and a load. Because when we're talking about Thevenin, what we're saying is we have our circuit and our impedance, and we're going to put a load in here, Z load, and we want to know what should the impedance of that load be in order to get a maximum power transfer to the load. And we get maximum power transfer when these two things have the same resistance, so we want this to have the same R as this, and we'll get maximum power transfer when we get rid of all the reactants in the entire circuit.
Alright, makes sense in the sense, well, I understand it. After that, it's
Okay,
just, like, I get the idea that if the, is basically the impedance of the Thevenin circuit is, or rather the imaginary parts cancel out, you end up with the maximum power.
because all your power is real. Okay, so what happens is your supplied power is the hypotenuse of a triangle. That is your supplied power. And that's what you have to make. And your real power is one side. It's also called average power. And your reactive power that you don't get any work out of, that's Q. The reactive power is the other side of the triangle, and your supplied power over here is S. And so if you keep this, if S is the same, so if you can supply a certain amount of power and you lower Q, then all of that gets to be P into your real power. So like, let's say this is the amount of power you can supply. This is what you get work out of, the real power. And you want to get as much of that as you can. So what you want to do is you want to make that Q part as small as possible for a given length, so for a given supplied power. If you can make Q as small as possible, that'll make your average power as big as possible.
Okay. Yeah, that's making more sense. So
I kind of thought you would like that depiction of it better.
Yeah, it's like a limited supply of power.
Right. You can only supply so much. And when you do, some of it's going to real power that you can use, and some's going to reactive power that you can't use.
And so would the reactive power kind of be the component of the power transfer that, where basically, because you got stuff that's out of phase, and so to a certain extent, it causes the waveforms not to play well together, which causes them, I guess, to like fight each other. Not fight each other. Basically, I'm saying that the reactive power is dissipated somehow.
Right.
Okay,
Yeah.
that makes sense.
Yep.
So if we maximize Q here, would that give us power absorbed? Because your real is constant, the average power, that's a constant thing.
Right.
So if we looked at the same circuit but we maximize Q, that's still, it's not power supplied now because your power supplied is going to be negative because our Q increased. So wouldn't that be just power absorbed?
Q is
Yeah.
it depends on whether it's steady state or it's going through its like changes, right? Because if it's an inductor or capacitor, it's that value is changing constantly.
Well, but he's
average-
talking about at a particular time. If you maximize Q, I'd have to think about that. I can't answer that right now. I will think about it though. There are lots of things that you can do, and I have done them where you, did y'all talk about power factor?
Yeah.
So you want to get your power factor as close to unity as possible, and there are different things you can do to do that.
I just think given this depiction, it makes sense for that power supply to be some like phase magnitude in a complex plane. So, because you have the real and you have the imaginary,
Mhm.
so it's just power.
Mhm.
So if you wanted that imaginary to be greater, now
Mhm.
you're starting to.
Oh yeah, yes. That is correct. That is correct. And yes. Okay. So going on to the last one. Oh, the second to last one? There's 8. Are there 8 or 6? Yes, there's
8.
There's 8. Okay. Let me see what we really need to do. You have 6 on yours. This is a lot on this last one. Let me see what I need. Okay. All right. Let's do 6.
How much time are we going over your time?
I have to be home by 6:30. And what time is it?
5:15.
What is it?
5:15.
5:15. We have time. I need to leave. Need to be packing up by 5:45.
Okay.
What time is this test due?
7:30 tomorrow.
7:30 p.m.?
Mhm.
Okay, plenty of time. Okay, so transfer functions, which is what you do in controls. You do a whole lot of transfer functions in controls. So you have a voltage transfer function. GV. Do you know what letters y'all use? Y'all use G or H? So GV, your voltage transfer function which is voltage gain, is V out over V in. These are all in the frequency domain. These are Laplace transforms of things in the time domain. So these functions are all functions of j omega. You will also see them as functions of s, where s is j omega. You also have a current gain. So current gain would be I out over I in. And that would be GI. What's that? G, okay. Then you can also have something called transresistance. Or transimpedance. And if you think about what resistance or impedance is in terms of voltage and current, you would get GR equals V out over I in. And you can also have transadmittance. And that is, admittance is the reciprocal of resistance. And so you have GY is I out over V in. Okay, so for the RC network below, define the voltage transfer function as V out over Vs, and VO is given as the voltage across the capacitor. And we know that in this particular circuit, we have our total impedance is R plus minus J over omega C.
You said define, that was just a given definition?
Yeah, it's just saying you can always, people will just give you a transfer function. Given this transfer function, do stuff.
Okay.
Okay. So we know by voltage division V out equals V source times ZC over Z total. And that is what we're looking for. So V out over Vs equals Zc over Zt, which is minus J over omega c over R minus J over omega c. And then what you would do is you wouldn't leave it like that. You would multiply top and bottom by omega c. And then you get minus J over R omega c minus J. And we really want our J to be with our omega, so I'll multiply by J over J. And this gives me 1 over RC J omega plus 1. And so problem 7 continues from this. And is asking about doing a Bode plot for this. This should be helpful. Yeah, let me just continue with this. This should be helpful. This should be very helpful. All right, so let me continue with this. Okay, so we're now setting R to be 1 kiloohm. And C to be 0.1 microfarads. And we can get our corner frequency. So if you remember when we were doing these Bode plots yesterday, when we had something that looked like this, 1 over 1 plus J omega over 10, and we were using that 10, that's called a corner frequency. And so to get this in that form, we'd have 1 over 1 plus J omega over 1 over RC.
Can you repeat that for the Bode plot?
Yeah, we want our factors to be in the form 1 plus J omega over omega c, where this is called a corner frequency. So we already had our 1 plus, and we have our J omega. We just need to get our constant in the denominator. It might be easier to see that if we plug in numbers. So let's just plug in our numbers. So I have 1 over 1 plus 0.0001 J omega, maybe. 1,000 times 0.1 micro. I think that's right. And then to write that, that is 0.00001 is 1 over 10,000. So this is 1 over 1 plus j omega over 10,000. So that tells us our corner frequency is 10,000. And this would be a pole. And so that means when you get to 10,000, it starts sloping down by 20. So corner frequency is 10,000 radians per second. In hertz, the frequency is omega over 2 pi. So that'd be 1591 hertz.
I'm sorry, how'd you get it into that 1 over 1 plus j omega over 1 over RC? What did you divide it? Sorry.
So
1 over
RC equals 1 over 1 over RC. So if I had 5j omega, that's a 5 and not
inverse
an
of
S,
the inverse of
5j omega, write that meter, 5j omega is j omega over 1/5.
okay, next. Okay.
Yep.
Sorry.
No, it's all right, everybody. It's I was expecting that. Okay. Now we had our transfer function. We had it as 1 over 1 plus j omega RC. And its magnitude, the magnitude of G equals 1 over, this it takes a while to prove, but it would be nice if you believe me. It equals that. And if we're looking for omega much less than omega c, see you. I'm not going to do the rest of this. Instead, I'm just going to see how we would draw the Bode plot for this. So, how would we draw the Bode plot for our function right here? So, if we had this, so if we had 1 over 1 plus 0.0001 j omega. Where's my MATLAB? So you had the sample code in class, and so you can get that. That's just right on your course. Let me get it. Show y'all where it is.
You just copy and paste it.
Yep.
And you adjust this,
So go to
it's at the bottom.
codes.
Yeah.
And this is your MATLAB right here.
Yeah, it's the code. You click on it, it's going to show the code.
Mm-hmm. It just gives it as a text file, I think. Or maybe it downloads .m. My computer's getting very laggy.
Yeah, I know this.
So,
You need a memory dump.
yeah. It's not having fun doing Zoom and video recording and OneNote, and now I'm telling it to start MATLAB. I don't see MATLAB yet. There it is. Okay, so that is the sample code from class. Now, this is interesting. What was our corner frequency?
Corner frequency
One
was
over 10,000.
It's actually
It'll be-
10,000.
Yeah.
So it's actually 10,000. And so last night we were talking about, well, would we ever have to change this top one? And I said, oh no,
yeah,
it goes up to 1,000, but we need to make this a little higher. And make this go up to 10,000,
So that's our range at the top, right?
right? And I'm going to change this from 0.01 to 0.1, so I'm not calculating as many points.
Okay.
And then our transfer function is just going to be, our numerator was just 1. And we weren't multiplying times anything. And I just have 1 divided by S1 plus point. Oh, no, that's not what I had. What did I have? I had 1 plus zero point 0.00001 times S1 plus 1. I got an extra parentheses there. So angular, so I want to take this out even farther. You see, it's like,
Right at the end, you just go,
yep. So I'm going to change this to 10 to the 6 and change my step to 1. There we go. Yeah.
That's a high pass filter.
This would be a low pass filter.
So it eliminates the highs, so it's a low pass filter.
Right, it lets the load come through.
Okay.
And make sure I'm telling you right. Hold on. I'm pretty sure.
I always get them all mixed up.
This is a low pass filter. Yep.
So it's letting the low pass, low frequencies pass through.
Mhm.
And it says low pass filter again.
Yeah. That's why I was pretty sure I was right. I'm going to, just for fun, I'm going to change this even more just because I want to see more of the behavior. It's not going to change. I mean, we only have the one corner frequency, but just, and then you can see that the straight line approximation, that right at 10,000, that's where it starts making a negative slope, a slope of negative 20 decibels per decade.
That's the corner frequency.
The corner frequency is the 10,000.
And it slopes down because it's in the denominator.
That's right. Yeah, so just to see if we really learned stuff last night, which it sounds like we really did, if we changed this to be that without a denominator, so we just had a 0 and no denominator,
So it should just go up.
and look at what happens if I square it, if I can remember how to do that in MATLAB. Is it just the square?
I haven't taken that yet.
I don't know if you can tell, but the slope doubles. It now has a slope, you see it's going from 0 to 40 over 1 power of 10. And before it went from 0 to 20 over 1 power of 10. So that when I squared it, the slope doubled. And so this is not squared. And over 1 power of 10.
Yeah, it's taking a lot longer to get to the 40.
All right. Well, I think I'm going to stop here. I think I did y'all some good.
Yes.
So, all right. Well, good luck.
Thank you so much.
Mhm.